All right. Well, thank you very much for having me here at a great event with a great theme. I love it. It's great to see new ideas, diversity, and all this being brought to events in a field that sorely lacks this very often. I'm going to jump right in, though. This is great stuff. I love this. So this topic today is all about analytic data. This is the source of what all the decision making we do comes from, and we're going to talk about ways to store analytic data in SQL Server more efficiently. And it's a great tool because it comes with the product. So if you have SQL Server, you have this. It comes with it. It's free. You can just use it. And if you don't, and you have large data out there, things that are tens, hundreds of millions, billions of rows, whatever, consider this because it'll make your life a lot easier. All right. So who am I? This is who I am. I've been speaking and writing on SQL stuff for a long time, working with data for a long time. I have written books and articles, done lots of things. Feel free to contact me. My info is at the end of the session as well if you want to contact me. This is me with my funny SQL Saturday umbrella. I've run the SQL Saturday out in Albany for a long time. We make fun swag and give it out. I'm sure hopefully some of you have it out there. Also, this session is recorded. You can watch the recording later, and I will post to the chat at the end of the session a copy of the slides and the SQL, the demos. If you need it, feel free to grab it and just mention where you got it from. And with that, let's jump right in. So what are we going to do here today? We're going to be talking about Comstor indexes, but to start with, we're going to quickly review what is Olap data, what does it look like, and what are your options for storing it. We're going to intro Comstor indexes, what are they? And then we're going to dive quickly into a lot of best practices and guidelines, things that are not well documented by Microsoft, that may not be well documented in articles you read, but are very, very important to getting the most out of this tool. We're going to talk about maintenance, and then a whole bunch of other questions and frequent options, things that come up that people ask about or talk about. We'll kind of run through all of that, wrap up, finish, and you're off to more sessions at this great event today. So where do we put our Olap data? And we have a lot of choices of where to put it. No matter what kind of data you have lots of choices. You can throw it into an unstructured data repository, something like a data lake, where you just take tons of data, throw it into documents, throw it into the lake, and use it. And for something very unorganized or for very ad hoc reporting, this makes a lot of sense. If you have data, a mountain of data, you're not really sure what you want to do with it yet. You don't know how to structure it, if you want to structure it at all, and you don't know how you're going to perform analytics against it. You're basically going to just play with it or run lots of ad hoc workloads against it. Something like this makes a lot of sense. If you have a little more structure in your data, you can consider a data warehouse, something like Analysis Services or Redshift or something else. There's many products for that out there. You can take your data and push it into a cube, and then your data is structured and can be queried very quickly. There is a plethora of third-party analytics software out there. If you have data, there is somebody out there who will be happy to take your data from you, put it into their product, and charge you some money for that. And if you know of a product that does what you want, or you use a product that does what you want, that's perfect. But it may or may not be what you want. The upside is that they do all the work for you. The downside is you're tied to their product and it costs money. Other options that are commonly used are Oltp tables. Very often data starts off small. We put it into transactional tables. And that's great until it gets big. Once your data gets into the millions and billions of rows, a transactional table becomes less and less scalable and less efficient. And the last option, one we're going to really talk about today fully, is putting data in a relational database into an analytic table. So this is not analysis services. This is nothing to do with integration services. This is nothing to do with other products. This is you store it in a table in SQL Server, and you give it a special data structure that makes it fast for analytic data. So what is a Columnstore index? Why are we here? And what this basically is that Olap data structure. So this takes your data in your table in SQL Server and turns it into an analytic structure. So it isn't just an index. This isn't just another binary tree you slap onto your data to make it a little bit faster. This fundamentally changes how your data is stored and is built for big data sets. If your data set is under 5 or 10 million rows, this probably isn't going to buy you much. Maybe a little, probably not much. The bigger your data gets, the more this helps you. This can increase your speeds a ton. Microsoft talked about 10 to 100x, and people always laughed it off and said it was a marketing thing, but it's not. You can really make queries go 100 times faster easily against your analytic data. And the technology underlying this isn't brand new either. Comstor indexes were introduced a while ago now, but the technology predated that in products like SSAS and Power BI and Power Pivot. So this is technology has been around for a while and has an opportunity to improve for years and years. And one of the keys to this is this is natively supported in SQL Server. And that's beneficial because it means that you can keep your data in SQL Server. If your transactional data is already in SQL Server and you want your analytic data to be close by, it can stay in SQL Server and you can query it quickly. And that's a huge deal. Not everybody wants to take your data, and begin splitting it out and putting it into different places. It's convenient to have it all in one place. All right. So what makes Comstor indexes fast? And there's many, many things that make them fast. It's not just one thing. But number one is compression. This is a huge deal. The data within a Comstor index is compressed in many different ways. There's just one algorithm. There's many. And because it uses different algorithms, dictionary lookups and pattern recognition and all kinds of other ways of taking larger pieces of data and shrinking them down, because of that, it shrinks your data a lot. And the more repetitive your data is, the more it shrinks. And it doesn't matter the data types. You could have strings, you could have characters, you could have dates, you could have integers. It all compresses very, very, very well. And you'll find the compression ratios can be 10 to 1, 20 to 1, 50 to 1. It really depends on the type of data you have and how repetitive. But the real key to the compression here is that your data remains compressed until you need it. So it's compressed in storage, wherever that storage happens to be, and then it's compressed in memory when it's read into the cache. So your data stays compressed until you actually need to query and get it. Because of that, you save storage, you save memory, and that is a big deal. And that's one of the things that makes everything faster, because the data is smaller, you can move it faster. If you can move it faster, you get it faster, your queries run faster. Life is good. Let's quickly run through our setup here. There it is. Great. So a lot of the setup here has been done already today, because you don't want to sit and watch me populate a 25 million row table. We don't have time for that. So here's what I've already done. We will run some live queries and show how these things work, but the setup is already done. So I created a table here called fact order big. This is not a Columnstore index table. It has a PK on it, classic clustered PK. I insert a mountain of data into it. I put a non-clustered covering index on it so that we can actually query by date. And then we can ask, how much data do we have? And the answer is we have about 23 million rows, and it spans a date range of like 4 years. Do note that when I run that query, just getting a count and a min and a max took a lot of reads to do that. And I have a speedy machine here, so hopefully it won't take too long, but it still takes a lot of resources to do it. So that's our first example. Our second example is, what if we take the same table and page compress it? So classic SQL Server page compression, which does quite a bit of compression, but it's limited to each page. Each page contains rows. Each row contains all different values for all different data types based on your table. So same setup as before, same table as before. The only difference is with data compression equals page. I insert my giant glob of data. I put the covering index on. Great. We now have that example. Next example is going to be the Comstor Index. We're setting everything up here so we can experiment and play today. So here's our Comstor Index table. I create a table. I insert a mountain of data. And then finally, I put on it a clustered Columnstore index. So most of our work today will be with clustered Columnstore indexes. We will talk about the non-clustered ones as well later. We'll start with clustered. A clustered Columnstore index is by default the data structure that defines your table, and it's on every column. So you don't specify columns. Every column in the table will now be compressed using Columnstore compression. Once again, how much data do we have? Same amount of data, same date range. Is the same data set for all of our examples here. Do note that it took a lot less reads, about a fifth of the reads, to get what we needed. Now let's, for the sake of compression, to really discuss the compression piece of this, let's compare sizes. So we're going to take now, just run a quick query that'll go out and grab the size of these 3 tables. So we can see our uncompressed transactional table took about 5 gigs, of which about 4.6 gigs are data, half a gig is index. And then if we page compress it, we slice it into about 40% of its original size. And if we Comstor compress it, it's down to less than a 15th of the size. So note the difference here. The Comstor compressed table is down to 340 megs, whereas the original table is 5 gigs. That's a huge difference. Storage and memory. And imagine this data gets a lot bigger. Instead of being tens of millions of rows, imagine it was hundreds of millions, billions, 100 billion rows, the difference here will be much more dramatic. So compression's a huge deal, and I start with that to show how dramatic the difference is. But more things make Comstor indexes fast than just compression. Another thing is metadata. So a lot of metadata is stored in SQL Server about all of our objects, but with the Comstor index, the metadata is stored in line with the compressed data. This is key because it means that you can use it. It's accurate. This isn't an estimate. The metadata stored in a Comstor index is accurate. It contains information about the range of values, the row count, the size of your data, is it nullable or not, so on and so forth. And all that information is used by the query optimizer to make smart decisions. And unlike statistics, which can fall out of date over time, this metadata is accurate. So it can use it with authority, not as a suggestion. So what it does is it allows a Comstor index to be filtered very quickly, because if the metadata says that we have a certain range of values here, the optimizer can say, I know you have that certain range of values there, and therefore I can take that into account when generating an execution plan. What it ultimately does is allows for very fast filtering, and we'll demonstrate that later. But the metadata is very important, and I will display that in a moment. Another key piece to how a Comstor index works is batch execution. This is really what, in the background, can speed things up, because you're working with lots and lots of rows. Transactional data tends to be a few rows here and there, getting updated, inserted, deleted, whatever. But with a large amount of data, there's a benefit in batching data. So what happens is, under the covers of SQL Server, when things are processing in your execution plan, traditionally, before this existed, a single row was passed at a time through the operators. And it sounds slow, but it really wasn't that slow. But under the covers, that's how it worked. Batch execution allows for rows to be transferred from operator to operator in groups, which, when you're working with millions or billions of rows, makes a lot of sense. What this does is it reduces the amount the SQL Server has to pass control back and forth between operators to get data from here to here to here to results. The larger your row counts, the more valuable this is, and by default, this will be used against Comstor indexes. If you don't see it being used for some reason, it means something is wrong. But this is a key feature, it's very useful, and it's very easy to check and see if it's on and working. So very quickly, I'm just going to run a random query here. Give me some metrics from my data set, my Comstor index, for everything greater than January 1st, 2016. I run the query, I get results back very fast, and if I turn on the execution plan, I can look at it. And I can say, here's my execution plan. And an important note on the execution plans for Comstor indexes, you'll notice whenever you do any query against the Comstor index, it's going to show a Comstor index scan. Now, traditionally, we think index scans are bad. Index scan means I read the whole table, it was scary. That is not the same here. If you're reading from a Comstor index and you see index scan, that's the default operator. There is some requests out there to have some more granularity here, but it doesn't exist yet. So your only operator you'll ever see against the Comstor index is index scan, and that's normal. But I can check something here. I can hover over it and get my plethora of data back, my metadata, my information about my execution plan, and I can note on the third and fourth line, the actual and estimated execution mode of this operator was batch. And if I walk through, I'll see batch, batch, batch. Great. So I know batch execution is happening. If you're using Comstor index, you want it to be happening. And if it's not, investigate. Why is it not happening? Is there some trace flag on? Is there some query hint? Are we in a really old version of SQL Server? What's going on here? Cool. I'm going to just pause after each section in case there's questions. Otherwise, I'll just freight train forward, as is tradition.
No questions yet.
No problem. So it's not just reads that are faster in Columnstore indexes. Writes are also faster. This is huge. Bulk loading is something that typically, traditionally, is reserved for things like, BCP and other. I'm loading data from a file into SQL Server through some really awkward process. In a Columnstore index, though, when your inserts increase past a certain number of rows, 102,400, you will find that it will switch from a standard load process where everything's logged in the transaction log, row by row by row by row, to a bulk load process. A bulk load process is minimally logged. And this is what we want here. Most Olap data loads are going to be large, and they're going to be the sort of processes where if they fail, you just retry them. And so our desire to point-in-time restore into the middle of a data load is very low. As a result, bulk loading is perfect. What this does is it makes your transaction log growth much, much smaller during a load by an insert into a Comstor index, which greatly increases your speeds. This can make inserts into a Comstor index much, much faster than they were previously. And more importantly, it means that the convention against transactional tables that many people have of batching, many of us have seen that before. Oh, I've got to insert 1,000,000 rows in a transactional table. Let me batch it into 1,000 rows at a time. That convention does not apply here. When you insert data into a Comstor index, insert as many rows as you want at once. Insert millions of rows at once, and don't be afraid of that, because it'll insert fast. Any time being taken up during the process will probably be taken up by the read from whatever your source is, and not the write. So bulk loading is hugely convenient, very efficient, and makes inserting data into a Comstor index very fast. So now that I've talked a bit about some of the things that make these things fast, you're probably scratching your head and asking, how do they work? And really, to fully understand this big picture, you've got to talk about what makes Comstor Index fast, what is the architecture, and then let me show you how it works. Those things will help make this a little clearer. So a Comstor Index is structured into what look like blocks here, and those blocks are segments. So you have groups of rows called row groups. A row group's up to 2 to the 20th, or about 1,000,000 rows. So by default, automatically, SQL Server will take your data and segment into, will partition it into rows. Both the word segment and partition aren't really ideal here. I'll just say groups it into rows. We have row group 1, row group 2, so on and so forth. Each row group has around 1,000,000 rows in it. And then, within each row group, each column is individually compressed into what's called a segment. So data in a Comstor index is compressed individually by column by column by column, which is why the compression is so good, because a column will have very similar values in it, whereas a row will have a whole variety of stuff. So this is kind of what it looks like under the covers. You have row groups, you have segments, and the number of total segments you have in a Columnstore index is equal to the number of row groups times the number of columns. So if you have like here 6 columns and 4 row groups, that's 24 segments. If you have 10 columns and 100 row groups, it's 1,000 segments. This is all represented by metadata. I mentioned metadata earlier and how metadata can help speed things up. And it does. There are views in SQL Server that are invaluable for understanding how a Comstor index works. The first one is Columnstore row groups. It's a system view. I join a few other views here to get some metadata about tables and indexes, partitions, and stuff. But ultimately, the new view is this, Columnstore row groups. This gives me a row per row group and tells me, hey, here's my Columnstore index. For each row group, here is the state of it currently, the number of rows, the size in bytes. And there's more metadata out there besides this. This is just a start, though. But this is the beginning, though. This tells me how many rows from each row group, which is important. You want to know how many rows are in there and how big they are. This tells you your size per row. You can divide your size in bytes by number of rows and get your row size. Great. How about our segments? Again, one more new view. sys.columnstore segments will give us a row per segment. I'm going to use these views throughout the session today, so don't feel like I'm going to introduce these and forget about them. We're going to use them over and over because they're very useful. All these queries are available later. Don't feel like you need to type very fast right now. This will all be available later to download. So this view provides one row per segment within each row group. So we have a lot of rows here. There's 456 segments in this Columnstore index. We can see all the columns are here. And we can see different IDs and information. Is there nulls? What's the row count? Dictionary lookup information is here too. Mins and maxes. If it's an integer kind of number, they'll put the min and max number here. Otherwise, it'll be dictionary lookup. That way you don't have to repeat the values over and over. So if it's a string column, it's repeated over and over. It won't write the same string column over and over. That's inefficient. It will create a dictionary lookup, and you'll reference the dictionary lookup instead. So you basically know your min and max values for every segment, which is extremely useful metadata to know, because if you search for a value that's not in that range of min and max, SQL Server knows I don't have to go there, which is very valuable. So that's the brief intro to metadata in a Columnstore index. We'll dive in more later as we begin to analyze Columnstore indexes and look at them. And I have a lot of demo here because live demos are fun, right? We all love live demos. They can work or break. And when they break, they're great laugh tracks for later. And because these things are all recorded now, those laugh tracks are very permanent. So this structure of a Columnstore index makes for very useful ways to slice out data very fast. The power of a Comstor index is you don't have to scan the whole thing at any one point in time. And the first way that we eliminate data so we don't have to read it is segment elimination. So let's say I have my hypothetical index here, and I write a query that says, select column A from the index where column B equals something. So I'm only touching columns A and B, and I'm not touching C through F at all. Normally, in a transactional table, you're still reading data from pages, and pages have all the rows on them and all the columns. You're forced to still deal with it. You can create indexes that cover the queries you need to avoid that, but that's a whole bunch of work, and it adds indexes to tables, and there's a limit to how many indexes you can throw on a transactional table. In the Comstor index, though, this behavior is automatic. If I query for just columns A and B, I will only have to read columns A and B. And so this column C through F in my Comstor index will automatically be skipped. I won't have to read them. I won't have to touch them. I will ignore them. And that is very, very valuable, which means that a Comstor index can scale out to many columns, and it won't get slower the more columns you have, because segment elimination will ensure that if you query for a few columns, you won't read the rest of them. And that's a very valuable way this works. And that allows us to slice horizontally. What's up? Nothing? Cool.
Not sure what that was.
Stuff happens. It's cool. Anyway, so now we can horizontally slice our data and get rid of unneeded columns, but there's more. Let's say our data is ordered. Let's say that we have data that we're looking for, and we only find that data in one row group. It does not exist in the rest of the row groups. Our metadata will tell us that, and that's great. So let's say in this example, I'm looking for data that only happens to be in row group 1 because my metadata says so, and I can then cut out and only query for row group 1. And so like before, if I run that query, SQL Server will ignore row groups 2 to 4 and not read all the data in them. This allows us to cut our data size down greatly vertically. So if I have lots and lots and lots of rows in my index, but I'm only searching for this, and my data is ordered by that, I can skip all the rest. We're going to talk about data order in a moment because it's very, very important in a Comstor index. But these two ideas, segment and row group elimination, are going to allow you to read this thing very, very, very fast because it can scale in any direction indefinitely, and it'll still be fast because it slices up the data you don't need. The key here, of course, is that you do both. I say, hey, query for columns A and B and give me a date range of only this one date range that's in row group 1. Well, cool. I do that, and now my 24 segments that I'd have to read before become 2. And you can imagine on the scales if this becomes millions of segments. And millions of segments is not unusual. A Comstor index can have billions of rows in it. So a million segments is not weird. If you had a million segments and I said I only have to read 100 of them, that's pretty amazing. I can ignore 90% of the data. There's a little bit more, and that is how do we write data to a Columnstore index? When these were first released back in the day, they were read-only structures. You built a Columnstore index, and you couldn't write to it. You had to rebuild the whole thing if you wanted to add data to it. And that was very expensive, and the reason it was done that way is because compressing a segment and compressing all the segments in row groups is very expensive. It's not a cheap process. So what we added to SQL Server to account for this was the delta store. So when you make small changes, so if you bulk insert lots of rows, they'll bulk insert right to the Columnstore index, minimally logged, super fast. If you make small changes, like some inserts and deletes of small numbers of rows, they're going to go to the delta store. And the delta store is just a heap. It's a B-tree heap. If you create a heap, it's just like that. The delta store sits on top of the Columnstore index and accumulates changes that occur via small operations. And then asynchronously, a process called tuple mover will come through every so often and push those changes to the Columnstore index. And what this protects you from is being hammered by lots of small operations. If I insert small numbers of rows over and over and over, I don't want to destroy my server's resource consumption because it's now compressing, decompressing, compressing, decompressing. So instead, what it does is accumulates those rows here and pushes the changes over. When you read from your Columnstore index, it will automatically read the delta store first and then overlay that on top of the Columnstore index. You may think for a moment because the delta store is a heap that it's going to be very, very slow. The reality is it isn't that slow. It's a little slower, but realistically, your Comstor index is going to have 100 million rows. Your delta store is going to have 100. So realistically, the speed set in the delta store is small. It's not going to really have a huge impact. But it is important to understand how this works and that it exists and that it's used by SQL Server to manage your small write operations, so you're not constantly compressing and decompressing an expensive operation segments. So with that, we can start talking about how writes work. Inserts are the first thing that become very fast in a Columnstore index. If you insert a small number of rows, they will go to the delta store. The exact number is 102,400, and you can demo this if you want. You can insert 101,399 rows to the Comstor Index, and you can watch them go to the delta store. You can insert 102,400, and you will watch it go right to the Comstor Index. And you can notice your transaction log grew a lot more when you use the delta store than the minimally logged process. So therefore, there's a huge benefit to running large batches. Insert 500,000, insert 1 million rows at once, and don't be afraid of that because that will be faster. So in general, aim for larger batches. If you're a huge nerd like me, you can try to aim for 2 to the 20th, but you don't really have to do that. That's just, absurd optimization. But in general, large batches are better. Smaller batches will be slower. And I'm not saying you shouldn't insert smaller batches. If you have a giant table with 1 billion rows, and you happen to insert 100 rows at a time, that's the way you do it. But there could be a benefit maybe putting that data into a temp table first, and then bulk inserting it afterwards. It's really up to you and how busy your Comstor Index is to take all these operations against it. Delete operations are not delete operations. What? Data is not deleted from a Comstor Index. What? The reality is data is soft deleted. So when you delete data from a Comstor Index, SQL Server will create a structure called a delete bitmap. One delete bitmap will exist for every row group and will overlay it and basically say, is this row deleted or not? So if you delete rows, they aren't deleted from the Comstor Index. Your Comstor Index structure isn't really touched at all. But instead, the delete bitmap will say, these rows are deleted. So when you read from the table, from the Comstor Index, it'll check the delete bitmap first and ignore those rows from your operation. In general, some deletes won't really hurt you that much. A lot of deletes will hurt you. Frequent delete operations will result in fragmentation eventually, assuming it isn't just the archival or deletion of the oldest data in your index. It can cause fragmentation. So just be aware of that if you delete tons of rows, you may eventually run into fragmentation and need to do a rebuild just to get rid of all that. And we'll talk about index maintenance later, but it's just kind of an important note that deletes aren't real deletes. They don't actually go away. The rows are there until you do more, which is the maintenance piece of it. And we can demo this and show how this works. So here is our Comstor Index again. Here's all of our row groups. You can see 24 row groups in the Comstor Index. And because I just created it nice and fresh, you can see that for the most part, they're all grouped into those nice 2 to the 20th rows per row group. And then there's a little less than a few other ones. Let's say I go in now and I delete 100 rows. They delete, no problem. They didn't really delete, but I deleted them. And what happens to them? I go here and I can see some stuff happened. I can see now that I have deleted rows that are flagged in my Columnstore Index for these 2 row groups. And I can see that the data they're stored in is a Columnstore delete bitmap. That comes right out of the sys.internal partitions view, which gives you some information on what's going on inside. And we can see 100 rows. So those 100 rows are flagged as deleted. If I query that data, my results will be correct, of course. But I can see they're not really deleted, though. They're only flagged as deleted. They're soft deleted. So that metadata that we talked about earlier can tell you details about how your data is stored and where it is and how many rows are deleted, which can be used to measure fragmentation in case you need to know that in the future. Cool. So the last operation you can do, you have inserts, you have deletes, is you have updates. An update is a delete followed by an insert. That hasn't changed. But the complexity is that you have to do a lot of things in one transaction now on a Comstor Index. You need to basically soft delete some rows, update your Columnstore delete bitmaps, and then immediately insert some stuff into the Delta store on top of that. And for SQL Server, that can get very slow. So in general, a great pattern for loading a Columnstore Index is to avoid updates at all costs. In fact, it is better for you, the developer, the architect of this process, to delete rows first and then insert them. So instead of updating 1,000 rows, delete 1,000 rows, then insert 1,000 rows. In general, you want to avoid updates in a large Columnstore Index at all costs. And I'll mention it again later as a best practice, but updates are not simple operations. They're not cheap. And as your index gets larger and larger, if you update across many, many row groups at one time, you will find that it'll be exceptionally slow. This is poorly documented, but it is known. It is well known. And it will hurt your server. Wherever you store your data, that SQL server will be in pain when updates are performed. So avoid updates. It's a good piece of advice. It's not a hard pattern to avoid. Just do a delete and insert instead, and life is better. And we can show this as well. I can go into the Columnstore Index. You can look at it again. Here's our row groups. We can see what the thing looks like right now. We can see we have 100 deleted rows, and then all the rest of the row groups are just what they were earlier. I can now go in and update a few rows. Update, done. And then I can show our row groups again, and we can see now there's more complexity here. So every time I do a delete or an update, my Comstor index is getting more complex. I can see that I now have 5 rows in the Delta store from the 5 that were just inserted, and 5 more in the delete bitmap, because an update is a delete followed by an insert. And this documents right here the fact that I deleted 5 rows and inserted 5 rows into the same table. So a little awkward, but that is how it looks, and you can check that and see how many rows have been processed in an update like that. No big deal. But in general, it's worth to avoid.
Couple of questions for you.
Sure, go for it.
This is a good time. All right. First one is there we go. Just refreshed. 1 second, sorry. Is Columnstore the index to rule them all? Should one only be using Columnstore indexes on all large tables and not other indexes on them?
Great question. In general, the best target for a Columnstore index is an analytic table. You want a large analytic table that services an analytic workload. So in general, you want a table with at least 5 or 10 million rows or more, maybe 100 million. And then you want a table where you do data loads infrequently, or at least very controlled data loads. And your read operations tend to be bounded by some kind of date range. So if you have 10 years of data, you tend to query analytic data across lots of rows over some limited date range. But even if it's not limited, it'll tend to be fast. So you want a table that is not a heavy target of updates and isn't deleted from too much unless it's just archival. But I wouldn't say it's the one index to rule them all. But if you have a large analytic table, consider this first before anything else.
Cool. Good stuff. Second question is, what about truncating tables?
Truncation is not a delete. It's a DDL operation. If you truncate your Columnstore index table, it's gone, just like a truncate from before. Is not a logged operation. It's minimally logged, sorry, and therefore it'll be fast. So you can truncate your Columnstore index or partition a Columnstore index. It'll be nice and speedy and no problem.
Awesome. We're caught up with questions. Back over to you.
Great, thank you. Questions are wonderful, and they're very good questions. I appreciate it. Now we've talked about the architecture and how a Columnstore index works. Now we can begin to get into best practices and how to make them as fast as possible. And this is the most important one, and it's not something that is very well documented. And intrinsically, you don't know about this. When you create your Columnstore index, you don't specify columns. You don't specify column order, at least in a clustered. In a non-clustered, you specify columns, but you do not specify order. So by default, there's no data order in a Columnstore index. If I throw data into it willy-nilly, it'll be inserted into the index in the order that I inserted it. So if I put 100 rows in from 2014, and I put 100 rows in next from 2021, that data is going to be all compressed together. So the reality is data order is whatever you make it. And row group elimination, where I look at that metadata and eliminate row groups, requires ordered data. If your data is not ordered, row group elimination won't be effective. It may still happen if your data happens to have some intrinsic order to it. But you want to order your data. You want to be in charge of your data, and you want it to be in order because it will cause you to have the best performance on these indexes. And typically, in an Olap environment, time is the dimension used for data order. So you will have your data in your warehouse or in your index, and it's going to start in 2017 and go through present. And every day you're going to load some more data, or every hour, whenever you load data, you're going to load the new data. New data is from now. So naturally, your data is going to order going forward. But you want to make sure your existing data is ordered as well. Well-ordered data will not just save you speed. It won't just make your queries faster. It'll actually save storage, and I'll demonstrate that in a bit. And it's going to blow minds because I still can't believe how much more efficient the compression of ordered data is over unordered data. So now we're going to jump into demos of how do we optimize the stuff and make it even faster. So once again, here is our Columnstore index. I'm specifically looking at order date key. So I have this Comstor Index here. It has 24 million rows in it of analytic data. I'm going to look at my segment data for just this one column, order date key. The min data ID and the max data ID are dictionary lookups, but they're still ordered. And so I know that lower means earlier and higher means later. The first thing I notice when I look at this data is the min data ID and the max data ID in every segment here are exactly the same. That means that my data is smattered across all those row groups unordered, so that if I want data from 2018, I have to go through every single row group. 2021, every row group. I got to scan the whole index, whether I like it or not, to get what I want. And SQL Server does help you in understanding how many row groups you read and don't read. If I run this analytic query here, give me the quantity, one column over a date range of 1 month, I get my results. And you can note, if I turn statistics IO on, I get some additional information. Segment reads, 24. Segment skipped, 0. This tells me no row group elimination occurred at all. I read every single segment to get what I wanted. And that is unfortunate. How do we overcome that? There's two ways. I create a new table here with the ordered suffix. Same exact thing as before. I create a clustered index though now, not a Columnstore index. The table's the same. I am creating a classic binary tree clustered index on this table. I'm now going to load in all of my old data that spans many years, loading all the data in, and then I'm going to take and swap my clustered index with a Columnstore index. This is an effective strategy for ordering a large existing data set from a transactional index into a Columnstore index. And drop existing on ensures that I immediately swap them, nothing gets in between. And max stop 1 ensures I don't have parallelism. Because if I insert data into a Columnstore index or build an index with parallelism, I may not end up with the data order that I want because data can be streamed and it won't care about order. So now I'm going to run a query, the same query as earlier, against my ordered Columnstore index. And one important note here is that data will naturally order. If your data is inserted every day, every week, every hour, every month, whatever, in order, and it's in data order, you'll naturally have ordered data going forward. This is for all the old stuff that you may be having in an old legacy table you want to convert to a Columnstore index. I look over here now and I see segments read 2, segments skipped 21. And so I skipped most of the segments in the table because I didn't need to read them. Now that the data is ordered, I can look at my metadata, and my metadata tells me, hey, these min data and max data IDs now kind of slowly go up. And so if I want a specific date or a small date range, I only need a small number of row groups and the rest can be skipped. If I only want a date from here, for example, I only have to read a couple of row groups and ignore all the rest. So ordered data is what makes row group elimination work, and it will speed up your queries greatly, and you can confirm it in statistics IO by looking at those segments read and segments skipped. So this is an important piece of how Columnstore indexes work, and you can make the most out of them with data order. Immensely faster queries. See if any questions. There's no questions. I'll keep going. The next thing we can do with a Columnstore index, which really meshes well with the data order, is partitioning. Classic table partitioning provides a lot of value to Columnstore indexes because your data is probably already ordered by date and time, and therefore it's already perfect for partitioning. And partitioning buys you a lot of other cool things, like the ability to do maintenance on a partition, whether it's index maintenance or a backup. You can archive data, you can partition switch, you can truncate, you can do all kinds of cool things on your data, partition by partition. And on top of that, you get partition elimination, which means that at a fundamental physical level, you'll now skip segments and row groups automatically, and you'll never even get to them. And that's really cool, and it's worth even demoing it. Partitioning is not something everyone uses, but if you have a table approaching, the hundreds of millions, billions of rows size, you may as well partition it. It will buy you performance, and it'll make your maintenance easier in the future. So I have all the code here. I'm not going to run it right now, but you can see I add file groups. I add files to those file groups, one per year. I create a partition function over those years. I create a partition scheme over my partition function. This is all well-documented stuff. If you've never used it before, feel free to reference this presentation or MSDN for more information on partitioning. There's tons of documentation on partitioning out there. I'll create my partition table. I'll put my index on it. I'll insert my data into it. This is just like before. I'll then swap the clustered column store into there, drop existing on, so therefore I can get my ordered data. And the only difference is I created my table on the partition scheme across order, date, key, column. Everything else is the same. So everything else is the same, but now if I run my same analytic query from before against this table, I get my same result. Note, segments read 1, segments skipped 2. So the rest of those segments are still on my Comstor index, but they're in other partitions, and SQL Server can automatically just partition and eliminate them and skip them, which makes my query do less reads. I mean, we're down to like 25 logical reads to run an analytic query across like 1 million rows. That's pretty cool. So partitioning goes hand in hand with row group elimination and ordered data. You don't have to partition if you don't want to, but it will buy you some more performance and make the administrators' maintenance jobs easier. Cool. So another best practice, ordered data is number one, by far the best practice to follow is order your data. Number two, I mentioned it earlier, I'll mention it again, avoid updates. Do not update a Comstor index ever. It may seem fast, it will not always be fast. Eventually, especially if your data is not perfectly ordered or it's fragmented, your updates will get slow. And you'll have to update 25, 50, 100 row groups all at once, and SQL Server is going to crawl. So do everything you can to avoid updates and rewrite them as delete plus an insert. And the biggest hazard for this is if you're migrating old code to a Comstor index, make sure you carefully search and check for any updates against that table and convert them to delete and insert. The end result will be the same, but it'll perform much, much, much faster. Trust me, avoid updates. Another best practice, this goes with segment elimination. If you read less columns, then all the rest aren't read out of your clustered index. You don't need any non-clustered indexes here at all. You don't need covering indexes in the world of a Comstor index. By default, if you query for 2 of 10 columns, you will automatically just read those 2 columns with the segments and ignore the other 8. So it's the best practice more than ever to query the columns you need. Don't select star, don't select extra columns. Skip any column you can, because every skipped column is one more segment you don't have to read for every row group you have. If you have 1,000 row groups, that means you skip 1,000 segments. If you have 1,000,000 row groups, you skip 1,000,000 segments, automatically 1 per column. Huge, huge deal. So query just the columns you need and nothing more. More cool stuff. You can compress your data more if you want. Columnstore archive compression is another step above Columnstore compression. It's not the default because it's more expensive. You get more compression than before, but it costs more computing resources and time to write, and a little more to read. But it makes your data really, really compact. So what is archive compression for? It's for cold storage, warm storage, data you don't touch very often, data you're probably not going to need much. It's there for posterity. Or maybe old data where if you do query it, you don't really mind if it takes a little longer to query it. And you can do it, of course, on a partition by partition basis. So you don't have to archive compress all your data. So if you have a giant repository that goes from 2010 to present, and all the data before 2 years ago you rarely ever touch, you could archive compress it. At the end of the day, it'll save space, and it'll save a little bit of memory. But again, if you're not hurting for space, you don't have to do it. It's an option. It's a pretty cool option. And we can demonstrate how much space it saves if we want. So I'll create more tables. Why not? I have, 50 minutes worth of table creation in here. This will be our archive table. It's ordered. It's clustered index. We insert our data. We clustered column store it. And we compare our sizes. So this query just checks our size of tables. This is going to check all of them now. I'm going to wait for it. Oh, I have my, oh, shoot. Ah, I've done it now. All right, sorry about that. I have my execution plan on right now, which is not something you want on when you run a query like this across lots of system views. So you got what you wanted. You got a little gaff during the presentation. You can enjoy it for life. Here we go. Here's every table we created today so far and how big it is. We can see that our original transactional table is 5 gigs. When I throw a covering index on there, pretty much the same idea. Page compress it, it gets smaller, about 40%. If we column store it and order it and partition it, you get down to this. If you put a cluster, oh, I have an index in there too, I forgot. I do have a non-clustered on there later. So the partitioned ordered is actually a lot smaller than that because there's an index in there. Our column store is 340 megs. Our archive compressed column store is 217. If you order it, it gets down to that. And if you order and archive it, it goes down to that. So this original table is 5 gigs. I Comstor indexed it. I archived it. I ordered it, did all this stuff. And the end result was a table that was a fraction of the size, a tiny fraction. Ordering it reduced it by 1/3. Just having ordered data reduced it by 1/3. And the reason is that data that is close in proximity time-wise will tend to be more similar to other data in close proximity time-wise. And so you'll find more overlap, more similarities, meaning your data is easier to compress. I won't say you have to archive compress. You don't have to. Save it for data you don't touch very often. But even just having an ordered column store index that's partitioned, huge difference. 5 gigs versus 113 megs. It's pretty dramatic. You won't always see this level of compression, but you can, and it's pretty amazing. All right, so maintenance. Everyone thinks to themselves, what about fragmentation? What about maintenance? How do you maintain a column store index? And the key to it is that if you have a very well-ordered insert-only column store index that is very rarely deleted from or updated, you will need almost no maintenance because your data will keep getting tacked onto the end. It'll go to the Delta store or into the column store index. It'll get pushed in order over time. What causes fragmentation, though? Ultimately, it's delete operations that are not ordered. So deletes in the middle of an index, or updates, because you're forced to delete and insert, or unordered inserts. If I have a data set that goes from 2015 to present, I insert data from 2016, I've now got 2016 data tacked onto the end with my new data. Those are the things that cause fragmentation. And the more you do those things, the more you'll see. Your options are a reorg or a rebuild. Your reorg is online. It's pretty fast. It's pretty painless. It won't interrupt operations. It will combine undersized row groups. It can process your Delta store, and it can deal with all that ghosted, deleted data that's out there. That's what that does. The rebuild is a rebuild. You recreate your entire column store index from scratch, piece by piece. That's expensive, but it eliminates fragmentation completely. In general, this is something you shouldn't worry about unless you see a problem in your analytics or you see latency. Don't do maintenance unless you need to. A regular reorg is not a bad thing. A rebuild you can probably save, though, until your data is done. If you have data that's by partition, you can rebuild your partition when the partition is complete at the end of a year. And that's another key to partitioning, is that if your data is partitioned, you can perform maintenance against different partitions whenever you need to, and not against the whole thing all at once. So just the real takeaway here, I'm not going to dive into maintenance too much. You can really look into this more. There's a lot of documentation on it, is that if you have an insert-only column store index, it's a very ideal analytic table where you just insert data on the end and keep going. You won't have to do a lot of maintenance, and you won't see a lot of latency due to fragmentation. If you do a lot of deletes, a lot of updates, and you perform one-time maintenance that makes a lot of changes to your data, you may want to consider some one-offs, reorgs, or rebuilds. It's really up to you, but again, this is up to your tolerance for speed and performance. Don't feel obligated to throw this into your load processor, do it all the time. It's really up to you. A few more things to talk about here before we get ready for questions and wrap up. Non-clustered column store indexes. We didn't really talk about those very much yet, but you can take a transactional table and put a non-clustered column store on it, and it'll perform just like a column store index that we demonstrated today. A benefit is you can specify a column list and say, I'm going to put a column store on just these 3 columns or 2 columns. The upside, it'll make your analytics faster. The downside is they can become fragmented fast. If your transactional table is inserted, updated, and deleted very often, and it's not ordered by the same thing your column store index is ordered on, then you're going to run into problems. So the ideal place for a non-clustered column store index is a table that is transactional, but that tends to behave a little more like an analytic, like it's ordered by date, and it's not updated too often. Updates are very dangerous because an update will cause things to get fragmented. So a transactional table with not a ton of updates that's ordered will service the Columnstore index really, really well. The ideal solution, of course, is separate out your Olap and your Oltp if you can. Not everybody can do that, but if you can do that, you'll see ideal performance. But if you can't, test. That's the key here. Non-clustered Columnstore is not as much of a gimme as the clustered. So if you're going to use it, be sure to test very heavily. Test your read speed, test your write speed, test it in a production-like environment, and be sure that if you do this, it's not going to cause latency writing to the index or so much fragmentation that it isn't that much faster. So as always, test in dev QA, don't test in production. Demo that. I did create a non-clustered Columnstore earlier on a table. And I can run my analytic query against it. Now, if I put my execution plan on, I'll see that it used my non-clustered Columnstore index. Great. If I jump back here, I'll see 25 segment reads, 0 skipped. And 0 were skipped because this table wasn't happened to be ordered by date. And it's been updated a lot. So it's fragmented. And this is still faster than scanning a transactional table, but it's painful. For comparison's sake, I can look at a covering index and say, hey, if I were to run a query against a covering index, how would it behave? Index seek against a transactional covering index. And the answer is it wasn't much slower. It took more reads, but it wasn't that much slower. So one alternative to the Columnstore index, the non-clustered, is a covering index. Ultimately, it's up to you as the architect here to develop and test and decide what makes the most sense. If you're running very heavily, very frequent analytic queries against a transactional table, you'll probably benefit from a non-clustered Columnstore. Just keep in mind the caveats of updates and order, because that will affect your data. Question people love to ask, can you put a Columnstore index into memory? And the answer is you can, but you don't really want to. There are two very different technologies. The Columnstore index is optimized for large analytic tables. Memory optimized tables are optimized for heavily contentious transactional tables. They're not meant to go together, and if you do it, it probably won't perform better. I've seen one use case in my life where somebody created a lab-like case that proved it can be faster, but in reality, it will generally not be faster. They'll take up more space in memory because the structures in memory are not really optimized for this, and it'll probably be slower. So don't combine these unless you can think of some amazing reason to do so that isn't Frankenstein. Don't do this. Comstor Index's memory will not be faster usually, and they'll probably just be a headache for you. And they'll waste memory. They'll waste RAM. You don't really want to do that. It's important to know performance. Many people say slap your Columnstore index in your table, forget it, and life is good, or it'll make your life better, all your wildest dreams will come true. They might, but they also might not. In the end of the day, reading a segment into memory takes time and resources. So the speed of your queries against the Columnstore index will be based on how many segments do you read. Therefore, you need to rely on segments and row group elimination to shrink the amount of segments that you read into memory. If you order your data, it'll get smaller and more efficient, and you'll read less rows. If you query less columns, you'll eliminate all the rest of the columns, and you'll read less data, and that's huge. Load your data with minimal fragmentation, so do as few updates and deletes as possible. If you got to do them, you got to do them. I'm not going to say you can't do them, but it will cause fragmentation. And do your best to use row group and segment elimination. And also, make sure you have enough RAM. If you're querying a Columnstore index, make sure there's enough memory available to read segments to memory, because if you don't have enough memory, it's going to be constantly flushing stuff in and out of memory. It'll be slow. And you can test that very easily by saying, oh, I typically query my most recent year of data. How big is my recent year of data? OK, I know how big it is now, compressed in my storage. I want at least that much memory on top of whatever else I already have to support this. So performance is important. These are ways to make your performance faster. Don't forget best practices. They make our life easier. So to kind of wrap up and give us like 5 minutes for questions, Comstor indexes are amazing tools. They fundamentally change how you store analytic data in SQL Server, and they allow you to store your analytic data in SQL Server, which can be huge if you want to keep your data there. You may not want to put your data into a third-party tool or an analytics tool, or you may, for security and privacy reasons, want to keep your data near the source for easier data movement. So lots of benefits to storing your analytic data in the same place as your transactional data. They can improve your speed so much. It's unbelievable how much compression and how much speed you can get out of a Columnstore index. And while it isn't quite just slap it on and forget about it, in general, you can get a lot of speed out of it. And with a little bit of tweaking and best practice, make it very, very, very fast. And the key here is that this can scale. This can scale indefinitely. You can have billions, tens of billions, hundreds of billions of rows, and this can be fast. And that's something you couldn't do before easily in a transactional table. So it's an amazing tool. It's one I've personally used in production environments over and over and over, and they still kind of amaze me to this day and make me smile. And so with that, I'm going to turn it back over for a little bit of Q&A before we wrap up and go about our days.
Awesome. We have a good question for you. Are there any special considerations for Columnstore indexes when databases are in an availability group, especially in terms of implementation?
Not really. I would say, again, just make sure your data is ordered and try to avoid the big ugly updates, because whatever you do on your source database will be amplified and obviously put to your targets. You have multiple targets. Whatever happens in your source database will get pushed to your targets. So I really just recommend avoiding updates when possible, only because that will cause the most churn. But otherwise, no major considerations. Data will be applied in the same way at the source as the target. So a minimally logged insert will be minimally logged at your target. So really just follow your best practices and things should perform well. Test, of course, but best practices will take you to your goal, I think.
Awesome. We've got another question. Can you recommend any books about Columnstore indexes? Maybe in your book?
That is a great question. I've written articles in Comstor Indexes that are quite extensive. I have like a 4-part series on Simple Talk all about Comstor Indexes, and I would recommend it. As for book recommendations, I do have one. I do not know all the details off the top of my head, therefore I'm not going to make a fool of myself. But after this is over and I post the links and information and the files, I will add that in as well as a suggestion.
Awesome. Thank you. You've got a just some feedback. Wonderful session. Thank you.
Thank you very much for having me today.
Yeah, of course. Thanks for presenting. Oh, lots of claps.
If there are any more questions, here's your chance. You got 3 minutes. If anybody has any questions they want to ask, free advice. Who doesn't want that?